call it quit, throw away the experiment, or you can analyze all the data that you have as a whole and look at how the trend is in terms of the growth of the tumor over time, and see if there's any differences in the rate of the progression or the rate of the growth of the tumor rather than the size of the tumor at the end of the experiment. Now, to do that, so basically, you have the data points from day 13, 14, 15, 16. It's a time series of these data points. And from these data set, you extract the slope of the data for each animal. They extract the intercept for the data set of each animal. And then when it comes to the final analysis, it is the analysis of the slope and the intercept. So it's basically, you have a latent variable that represent all this data at the bottom here. So with this type of method, you would be able to discern that there's truly statistically significant difference in terms of the rate of growth among these different graphs. That if you only analyze the tumor size at the endpoint, that you may not be able to reach statistical significance. Another way to deal with the tumor analysis is that at the end of the experiment, you excise the tumor and actually weigh the tumor and have the wet weight of the tumor for analysis. Now, this is a good way because now when you use a caliper to measure the size of the xenograft when it's still on the nude mouse, the variability of the measurement sometimes can be quite wide. And because of the wide variability of the measurement, it limits your ability to detect a statistical significant difference because you would require a much bigger true difference in the size of the tumor in order to detect the statistical significance in a small number of animals. Whereas if you use the wet weight of the tumor, the wet weight can be measured down to the milligram. It's a very precise and accurate measurement. It lowers the variability and the chance of having a statistical significant measurement is better. Now, here, so in this experiment, I have 1, 2, 3 groups. Okay. So for the wet weight of the tumor of at the end of the experiment, okay, is the t-test the correct test for this situation? The answer is no, because I have more than 2 groups. So the t-test will not be appropriate. So in this situation, I used a one-way analysis of variance, one-way ANOVA. So with one-way ANOVA, if I want to know exactly is this group significantly different from this group, then I would need to do what is called a post hoc intergroup comparison. Okay. So with the post hoc intergroup comparison, using when you do that, the computer would give you a choice of several different tests. Okay, so depending on whether your data is normally distributed or not normally distributed, it will make a recommendation as to what test to use. So in this case, the data is not normally distributed, and then we use the Tukey test and come up with the p-values for the differences between the 2 groups out of the total 3 groups. So I'm going to conclude For scientists, okay, why do we want to be scientists? Okay, because we want the truth. Scientists are seekers of the truth. And statistics is a fundamental part of the scientific method. And you need statistics to help you to separate fallacies from the truth. And if you don't know statistics, you don't know science. You cannot be a good scientist. Okay. And this is the Latin works. Okay. I don't try to pretend that I know how to pronounce Latin, but anyway, truth conquers all things. Okay, so now we're open for questions, and I would like to ask you, what is wrong with this graph? Okay. Anybody that can point out an error in this graph or recommend a alternative way of presenting the data will get bonus points. Anybody?
So the first thing I can recognize is the unit of measurement. I think it's like 24 hours, 48 hours, and the third one is 7 days.
Yes.
The second thing is like at the first part of the graph, like 0, so the tree graph is like, it's not really separate, so I cannot say if it's really different or similar.
You mean here?
Yeah, that one.
Okay. So this is not really a true scale. Okay, it's not a quantitative scale. This is
That's right.
grouping. This is they are trying to represent this as a group that had no drug, the group that had 1 millimole, the group that had 5 millimole. And this is not a continuous scale.
Oh, yeah. Yeah, but
So indeed, that is one of the big issues that I have with this. Okay. Anybody else want to try? Somebody keeping track of the bonus points?
I think the first thing the same for here, this is just one group, and we just want to know about the concentration of metformin and the different trees about the hours. So I suggest that we can utilize that so we can see the durations of the treatment before and after treatment. But when you just like that's graph, so you don't know what happens before and after treatment. And I suggest you like a graph.
Okay. The assumption is that in the absence of any treatment, there would be no change. It would be all at this level.
Yeah.
So my issue with this graph is that one thing, this is not arranged in the quantitative manner. I think that the data points should be plotted on a continuous horizontal axis. Okay. So to do that, there are a couple of ways to do it. Okay. So this is depending on what the author is trying to convey. Okay. Is the author trying to convey a dose-response relationship? Okay. So if the author is trying to convey a dose-response relationship, then this horizontal axis, okay, need to be in the logarithmic scale. Okay, need to be log dose, log concentration. Okay, so from 20 to 10 to 5. Okay, just evenly spaced. Okay, but one is not. One is there on a logarithmic scale. So I think that if it's plotted in the logarithmic scale, it would be better to convey the dose log dose response relationship. Okay. Second thing, there's also the author is trying to convey the difference of the time, the duration of the treatment. So the conclusion that they're trying to make is that with this drug, with this drug treating this particular cell line, there is a dose dependency as well as a time dependency. Okay, so in order to convey that relationship, I think they should plot the dose response curves. Okay, and label the curves with the different markers. Okay. So this curve will be lining up this way, another curve for the 48-hour data will be lining up this way, and the 24-hour data will be lining up this way. Okay. Now, there's one more problem with this. Okay.
I think the one error is the sign of error is the top of this paragraph.
Say that again.
I mean that one problem in this in this graph is the sign of error of experiments. Oh,
It's a star sign on top of the star. So, on top of the bar, there's two stars. I think that what you say is the star signal on top of the bars.
Oh, the stars on top of the bars. Okay. The star on top of the bars is supposed to represent those there's significant differences or not. Okay, that's what's in the legend. So when there's a star like that, what they wanted to say was that there's significant difference compared to control. Okay, but okay, what test did they use? Okay, what test did they use, and what did the error bars represent? Okay, so they used standard error they used the error bars to represent standard error, and they used the student's t-test. Come on, you have how many groups are here? And your student's t-test. Okay, so that's absolute no-no. And another problem with this graph is that they mislabeled it. It's percent of control, 1%? Come on, this is 1. This should be 100 there. Okay? All right, so don't believe everything you see in the literature. Okay? There are many mistakes out there. Other questions?
I want to ask about the outline spot. It's either I'm not how to say that. It's either maybe it's a case out of the average case.
No, these are not outlying spots.
I want to say that just like right skew and in the bell curve, and just like right skew or left skew, and yeah. And I want to ask about the exceptional case, just like the with the size, just like star.
Oh no. These stars do not represent it. These stars represent this label and whether that particular mean is statistically different from the control or not. Okay. So those do not represent the outliers. So you see the outliers usually in a box plot. Okay. So outlier wires will not be labeled in bar charts like this. Okay, that's all. Have a good day. Oh, yeah, you want to do any demonstration?
So let's take a 10-minute break, and then I will do a live demonstration how to use Graphite Prism. And if you want, you can download Prism right now. Just go to Google website and type Graphite Prism. Prism is Prism, and you can start downloading now. It's going to give you 1 month free trial, and